Hi everyone, I'm Jack. You've got me kicking off, and it's really a pleasure to be here with you all, especially introduced by wonderful PhD student Davide. So today, alongside Ashley and Jamie, we're going to be presenting on behalf of the Genie team. Obviously, there's three of us here, but there's actually a much larger team that contributes to this work. It's a really great effort from all these wonderful people. We're going to keep it hopefully around 30, 40 minutes in time for the talk. So if possible, if there's bigger questions, if we could save them to the end. But if there's any clarifying questions, then please do interrupt, because we don't want to just crack on, have people not knowing what we're talking about. So the goal of this work is to provide some sort of way of generating infinite environments for agents. But to really understand the context for why this is such an important topic, we're going to go back what seems like ages ago in our field, 11 or so years, to one of the first major breakthroughs for deep reinforcement learning from DeepMind in 2013, which was basically that after the introduction of the arcade learning environment, which made it possible to train agents inside all of the Atari games. This work from Vlad, Ni, and et al., which appeared in Nature in 2015, showed that you could actually use deep reinforcement learning to train agents to play all of these different games, and many of them at human level. And for the first time, agents were kind of discovering for themselves strategies to play things at a human level. And actually, there's a really nice example, if you ever have time, of the breakout agent, where it actually discovers the optimal strategy of going above and really discovering how to go far beyond just a simple strategy. A few years later, a much more complex environment, Go, given access to the Go environment, which we have as a simulator for Go, the same team, well, similar people, but from the same company, DeepMind, showed it was possible to actually get a superhuman Go agent. And now this is a much more challenging environment, because unlike a simple breakout task, it's actually a game that's been played for thousands of years, that humans play for their whole lives and still couldn't beat this agent. And so actually people thought it was many decades away. So this is context that most people are quite well aware of, but I think that the key thing we want to emphasize is that these are remarkable achievements in individual environments, but really what we want is a more generalist agent that can solve a variety of different environments. Because while this is very useful for chess or Go, it may not be able to then solve a completely different task. And so at DeepMind, one of the questions we're very interested in is AGI, which gets banded around a lot as a term. But I think there's a really nice paper that just came out that you would have seen a few of us talk about, which really kind of formalizes this across two axes, because a lot of people kind of add a lot of, there's a lot of mental overhead when discussing what it even means to have AGI. And so I think this is a really nice paper that came out a few months ago that shows across a couple of dimensions what it really means. And I guess on one side, like going down row-wise, you have the actual degree of competence. And then going from left to right, you have two columns, which show sort of the narrow and general agents. And so what we've really shown in this era, sort of 2013 to 18, 19, is that we're actually pretty good at getting really, really strong agents in narrow domains. So if we get an environment that is perfectly summarizing how to play Go, and it's very accurate, we can then use that to train a superhuman agent in Go, which we have got. However, if we want a general agent that can do anything in the real world, so for example, can set up a Zoom call, very challenging task, but it can also maybe like drive a car. We haven't really got a simulator to do all of these things. We haven't got an environment for all these things. And so although there is this emerging AGI, so very simple level, but general things like ChatGPT, how are we going to get those agents to be able to take actions that would learn to solve much more complex tasks in a variety of different domains? And so there've been a couple of prevailing approaches for this in the last few years, because this question has been one that really for the last 4 or 5 years has captured a lot of people's attention. And really what we want is this bottom right corner, so this ASI, which is adding another term, but broadly it means superhuman, but in a wide variety of tasks. And so one approach is, what if we just take all of the environments that we have and all of the data from all of those environments and put them all into one generalist agent? So imagine we take all of the Atari games we showed you before, all of the robotics tasks we have available, even some language tasks, and instead just distill all of those behaviors into one generalist agent. And this was done in 2022 with the Gato agent, which was short for Generalist Agent 1. And Ashley was the co-author of this work, so you can ask her more about that later on. And the idea of Gato was that it could just distill expert behaviors from all these different domains, and then you'd have one generalist agent that could do a variety of different things. And they actually showed generalization performance to unseen tasks. However, the challenge with Gato is that it's only relying on data that you have already from pre-existing environments. It's not going to learn something brand new, and it's not going to be able to solve tasks that aren't in the preset distribution. So it's quite similar to the issues we might have with a language model. Also, Gato hasn't learned this ability to really explore for itself and discover new strategies. So it doesn't have the ability to do online interaction and really discover completely unseen things. And so a project that I was fortunate to be a part of that was taking a completely different approach to generalist agents was called the Adaptive Agents Project, where it took this X-land environment where you have 25 billion tasks. So imagine this world, it's sort of 3D, there's a goal, and there's basically a set of rules that define how the world works. And the agent knows these rules exist, but doesn't know what they are. So it has to discover for itself what they are. But it also knows what the goal is. And the goal might be something like pick up a cube or combine some objects. But it doesn't know how to get the cube because there isn't one right there. So it has to, for itself, in a few trials, discover the laws of this mini world that's been created for it, and then solve the task as efficiently as possible. And so the idea of this is it would force the agent to learn things like how to experiment and discover new things. And so, as I said, the task kind of contains these different things. So initial objects, rules, and then a goal. And the agent will see the goal, but it won't see what the rules are. So it has to discover them for itself. So we have a video here. Hopefully it plays with Aaron. Yeah, so this is showing the first trial. The agent's observation is here. And you see it basically has to, quite fast, has to pick up the black cube, but if it combines the wrong objects, they'd actually vanish. And so it realizes on the second trial how to get the black cube, but it's done it in quite a roundabout way. It's gone like round this way, whereas it started here. So on the third trial, with everything it's seen in context, it can then directly go to the goal. So what this shows is a very simple example of an agent that has basically 3 trials, and it has all of its previous experience in context, but it does not learning from that. It's just keeping them in memory. So it can kind of try new things and then improve. And this is really exciting to see, right? Because we actually tested this compared to how humans would perform in the same tasks. And this agent was able to adapt the strategies and get better on the fly, purely in context. However, while this is really impressive progress, we've got a generalist agent that can distill a bunch of tasks that we already have and become a generalist. And then we have another agent that, given 25 billion tasks, can then learn to do a variety of things as fast as humans. To extend, it's not really amazing because at the same time, the ADA agent can't solve a completely unseen game. You can't put it in Minecraft. You can't make it drive a car, right? And then the Gato agent, well, the same thing. It can't discover completely new behaviors that aren't already in the data set. So what we really need is a far more complex and more sophisticated simulator that would enable this real generalist agent to emerge. And so the question that we've been trying to tackle for the last year and a half is how can we actually produce this sufficiently rich and diverse environment that we could get an agent that can do all of these different things. And so there's kind of a few historical approaches. One is just to onboard environments. Like imagine you just say, okay, I'm going to get this really cool video game just came out. I'm going to make it into an environment. Or you try and get some simulator from somewhere else and try and make it into a reinforcement learning environment. That's one option, but that does require manual labor. The next one is we can do kind of what we did in Ada. We could just design a world and just make it gradually more complex. But being part of that team, it was super fast-paced and exciting, but it took a lot of work just to get that one environment that didn't really look that real and still lacked a lot of the complexity of the real world. And then the third option is we could just collect a bunch of data from people doing tasks. And this is what's typically done in robotics. But this also doesn't really scale because it requires human labor. There's this alternative approach for things, which is the bit of lesson, which many of you may be familiar with, which says that methods which scale with data and compute will ultimately outperform. So while we're having all these thoughts and we're doing this other work, in the meantime, you may have noticed that generative AI is moving at a pretty incredible pace. In fact, such an incredible pace that this 6-month-old slide is now very dated because we have DALL-E 3, for example, on video. I think it's safe to say we've got a little bit better than this. And then on text, I mean, there's a lot going on in text, so I'm not even going to begin to talk about that one. But this field is basically taking the opposite approach, and it's saying, let's take all of the unstructured data we have on the internet, and let's just train general models. So the question that we've been asking is how we get this general environment rather than just a simple language or image model. But what we want is to then use this approach of using large-scale data and compute. So we kind of have this paradox where we have reinforcement learning environments where agents can interact, and they have this breadth of interaction available. But they don't have the ability to generalize the unseen settings. Whereas foundational models themselves offer only limited interaction. You type in text, you get an image, it's done. maybe you keep doing it, but it's not going to then drive a car. But they do benefit from the breadth of internet data. And so can we kind of take these two ideas and fuse them together to get unlimited supply of possible environments for agents? And so that's kind of the main question for our work. And I'm going to hand it off to Jimmy to talk about how we could potentially generate interactive environments using all of the videos on the internet.
Thank you, Jack, for that amazing introduction. Okay, cool. So what we're trying to do with Genie is really, we're trying to make a generative video model as a foundational world model. And to understand this statement, let's dive into each of these for Genie in a bit more detail. So for a video model, for instance, Sora, what you would do to train these model is you would collect video and also typically caption that describe the video in a lot of detail. So this is just a video that I got from the internet. And then along with it, that's like an instruction of describing what the action that is happening in the video. So this sort of regime, again, requires this sort of visual language modality to train these models. And because typically it has pretty high requirement on the kind of data that you have, because a lot of time, imagine if you just get a video from YouTube. A lot of time, the caption doesn't necessarily correspond to what the scene is describing. So typically, we would have to collect these description, or in some cases, for instance, Sora, people are speculating that they're sort of relabeling recaptioning these video, and that's very important for the training of these model. So having like fine-grained description of the visual modality, as well as long description to the modality, seem to be really important, and that's why we have very limited data in this regime. And then on the other hand, we also have these foundation world model. In this case, I'm using the Minecraft environment as an example. In this case, to put this in like more computer vision-y term, what you would have is a video, and then also for each frame of the video, you have a lot of metadata that tells you exactly what's going on in this video. And in this case, you have access to the action that the player is performing, in this case, assembling and turning left. I'm not sure exactly. I don't play Minecraft, but this is what I'm guessing that is happening. So because of this, it requires video and action labeled that correspond to each frame of the video. And as a result, it has even more limited data. So our vision with Genie is essentially, we want it to be both a world model and a video model. And the way that we're going to do this is by essentially throwing a lot of video at it without anything else. So it's just video data. And we're hoping that by doing this, it enables us to train our model with a lot of scale. So we can essentially make use of any video on the internet. And we're hoping that by doing this, we can train a general enough model that can generate interactive environments like these. So again, the mission of Genie is to learn a generative interactive environment from video that is playable by both humans and AI agent. So we want to take essentially the video from the entire internet. What we like to say in the project is we want to take the entire internet and produce another internet. And so downstream, what this model should be able to do is that it should be able to just take in any image prompt as input. And then we're able to, as human, interact with this model by specifying what action do I want to see in this frame next. And then it generates different feature based on what the user select. So that's sort of the high level idea. And now let's look at the model in a bit more detail. So the Genie model contains 3 different components. We have a video tokenizer, a latent action model, and a dynamics model. So the video tokenizer takes in all T frames of video as input. In our case, we use 16 frames of video, and it outputs this video token. That's a discrete video token. So it's a classic compression phase. And then we also have our latent action model down at the bottom that takes in this video, and it extracts this latent action from the video that should model the transition between any 2 consecutive frames in the video. I'll talk about how exactly it does this in a bit more detail. And then we have our dynamics model that takes in the video token as well as the latent action as input, and it predicts the future. So that's how the model is trained. Now let's dive into each of these components in a bit more detail, and I think things will make a bit more sense. So first of all, we have the video tokenizer. We use a VQ-VAE as per, I guess, standard literature. Actually, the literature typically use a VQ-GAN, but in our case, VQ-VAE is good enough. So we use a VQ-VAE to tokenize videos into discrete tokens. So it has this typical encoder-decoder auto encoder structure. And it takes in the ground truth video, which contains 16 frames, and it discretizes the tokens through a VQ layer. And then it reconstructs the video back to the 16 frames. And the model is trained with a reconstruction loss and a VQ loss and a commitment loss, just like a classic VQ-VAE. It's worth mentioning that here, slightly different from, I guess, a lot of the work in the literature, here we use a temporally aware architecture for encoder and decoder for the video tokenizer. So even though for each frame, we would generate one set of discrete token, these discrete tokens are aware of the history. And we have found that this is important for model performance. In comparison to like a spatial only tokenizer, this is better. Okay, now the second component is the latent action model. This is maybe the most interesting component. So here the latent action model learns to extract transition between frames in an unsupervised manner, and this is how it achieves that. So first, let's look at the encoder. So the encoder takes in the history as well as the future frame, and it outputs this latent action that leads to future frames. So it needs to encode the difference between the history and the future frame. And it's worth mentioning that this latent action is a really tiny bottleneck. So in our work, we only allow the latent action to take on 10 different values. So it needs to extremely compress this transition between the history and the future frame. And how do we learn this latent action? That's where the decoder comes in. So the decoder will take in, again, the history, but now it doesn't have access to the future frame. It only has access to this latent action. And then it needs to predict the future frame using just the history and the latent action. So you can imagine that in order for the decoder to be successful in predicting the future, the encoder will have to do a lot of heavy lifting in compressing what it considers as the most important transition between the history and the future frame. So at test time, we actually throw the decoder away. So we just use the encoder, we give the encoder the video clip, and then it will generate the latent action that model the transition between any two consecutive frames in the video. Okay, so now the dynamics model, that's when we put it all together. So the dynamics model will take in the video token, which we get from the tokenizer, as well as the latent action, and it predicts video token of the next, of the next frame. And yeah, so for the dynamics model here, we use the masked style decoder, which essentially means that at train time, we'll mask out 75% of the discrete token, and the model is tasked with inpainting the tokens that are missing. And then at test time, if you're familiar with masked, you're doing this iterative refinement thing, but it's not really that important for the purpose of just like explaining the Genie model. For now, you can consider it as like an autoregressive style generation, but the masked process basically just speed it up. And before we get to inference time, I want to also make a note of the architecture that we use. So for all of our modeling components, this is the video tokenizer, the latent action model, and the dynamics model. We use this one architecture, which is the spatiotemporal transformer. And this is essentially a factorized interleave spatiotemporal layer in the transformer. So the model, each transformer layer will take in the entire video as input, and then it we'll have like a spatial attention block where each attention map will just attend over the tokens within each frame. And then the output of that gets passed to a temporal attention block where each attention map will attend over one token, but across the entire time series. So the spatial attention dimension will be height and width, and then the temporal attention dimension is time by one. And by doing this, we're able to save a lot of memory in comparison to just imagining, I guess, performing attention over both space and time, in which case it'll be time by height and width. And then we have a feed forward layer as per standard. Okay, cool. So this is essentially our model. This is how the model is trained. And then what happens at test time? How do we use this model? Well, at inference time, we're given this prompt image, x1, and the tokenizer encoder will encode this into the discrete token. And then we also have this action, and this is where things can get interesting. So the action, there are two options. One option is it can be chosen by the user. So I mentioned before that the latent action can only take on 10 values. And this is partly for training the latent action model, because it's easier to have a more disentangled action space if you have a small bottleneck. But also, this makes the model more playable, because now the user can say, oh, between action 1 and 10, which action do I want to see next? And just give the model that value. So it can either be chosen by the user, or it can be inferred from the ground truth frames using the latent action model. So this is what we do when we're trying to evaluate the performance of the model. If we want to generate a video that looks exactly like the ground truth video, what we do is we reuse the latent action model to infer the latent action based on the ground truth video. And then here for A1, we'll just use the latent action that's predicted by the model. Okay, so we have the discrete token Z1, and then we have A1. And then
How do you get interpretable actions for the user to control?
That's a great question. So this is a bit of a spoiler for Ashley's part. So basically what happens is, because we're training on such a large data set, in our data set, there's more than 40 years worth of video or something like that. So it's a really big data set. And because of that, and it also contains 200 distinct 2D platformer games. So because of that, the model has learned to generalize. So it can have consistent action space across different environments or different prompt image. So basically, the user experience of using this model is basically like getting used to how to play a game, or getting used to learning the control of a game. So for instance, latent action 1 will consistently map to moving to the right. Latent action 2 will consistently map to moving to the left. So that's something that the user can figure out as they interact with the model. And Ashley will show more results on that. Okay, cool. So then the dynamics mask decoder will take in Z1 and A1 and generate prediction of the next frame, Z2. And this can then be passed to the tokenizer decoder, and it gets decoded back to a frame. So now, as a user, you can see what's happened in this frame. And then based on this, it can determine, oh, do I want to see this action again, or do I want to try a different action? So it's essentially a gameplay experience. So you can just autoregressively generate the next frame, just like following this procedure. Does that make sense? Okay, I think it will make more sense when Ashley talks about some of our results, and I'll just pass that on to Ashley. Yeah.
Thanks, Jimmy. Yeah, all right, here we go. So as Jimmy was alluding to, Genie was trained over a very, very large video data set. And again, remember, the purpose of our approach is to learn a generative interactive environment from videos that enables us to interact with it as if it were a game. So our data set consists of publicly available internet gameplay videos consisting of over like hundreds of 2D platformer games. So at 11 billion parameters, Genie can be considered a foundation world model. So you can give it images that it's never seen before and interact with them and completely bring them to life. Again, even though we've never trained with actions. And so this includes images that were generated through text, as you see here. So one thing that really sets us apart from typical video generation models that you might have seen recently is that Genie introduces this sort of fine-grained, frame-by-frame interactability. And so each of the videos that we show here are actually real gameplay from a team going into our model and actually playing from these text-generated images. So let's take this didn't switch. Does it switch if I do that? Yes. Okay. So let's take a look at some of the different kinds of trajectories that we might see within Genie. So given the same initial prompt frame, as Jimmy was mentioning, we can take a latent action that's come from a user and plug it into our model to predict the next frame. And the important thing to note here is that we're using this VQ model that enables us to learn a discrete version. So people can actually say, okay, I want to take latent action 0. Maybe that's going to take me to the left, or latent action 1, and maybe that's going to take me to the right. It takes some interaction to actually figure out how these things map to the real actions in the world. But once you do, you can just step into these worlds and get this sort of diverse gameplay that you see here. So again, this is showing us stepping into these environments and actually playing them ourselves. And so you can see that we're able to generate completely diverse trajectories, even though, again, we're not using real actions here, but we're learning them from videos alone. Does that make, oh yes, please.
Sorry, for example, if I play with latent action 1, it goes to the right. Out of 100 times I play, how many times you can really follow right?
So are you saying that, like, how long can we generate
No,
this
no,
sort of?
is it follow 100%? Exactly. Follow
Oh,
one?
yeah. So we have found that the latent actions learned from the model are consistent. So I have some examples that I'll show later that show that given different prompt images, taking the same latent action will lead to similar kind of trajectories. So there, we found that like latent action 0 often means, stay still or move to the left, or yeah, does that make sense?
I think 100% of the time is maybe like a bit of a stretch.
Yeah, I would say that.
It is generally much better than you expect. And I guess also the first time anyone's ever shown purely unsupervised at scale, it just emerges. I think it's much higher percentage than any of our team would have guessed, and we were the ones think it was a good idea.
Cool. So one of the most exciting things that we found within Genie, is there a thingy popped up? Okay, maybe it's fine.
Yeah, I think we can go back to the rest of the questions at the end.
Okay. Yeah, okay. So one of the most exciting things that we found within Genie is that it can be prompted on completely out of distribution trajectories. And so at some point we wanted to see if we can just take sketches and plug it into the model, even though it's only been trained on 2D platformer games. And so on the left here, you see a drawing made by Richie from our team. In the middle, Jeff Clunes, one of his children, made this sketch here. And the one on the right is something that nobody wants to claim, but I'll say, okay, I did that one. But I think the exciting thing is like, we were actually able to play these environments. So you can see that we're able to climb the ladder from this sketch, or move the football player to the right, or take this little blob character thingy and take it to the next platform. And so once we started doing this, it really opened our eyes to the kind of like creativity that Genie can actually enable. So from here, we actually decided to go a little bit crazier and try out like really super out of distribution, real world images that were completely unlike anything that our model had seen. So the left here, you see Jack's dog Doris and Tim's little figurine thingy there, my slice of pizza, and we wanted to see what happens if we plugged it into our model. And we're again able to control them. Now, of course, if we had actually trained on these kind of environments, we would probably see a little bit more controllability. But just imagine what we would see in that case. So it's quite exciting that Genie is able to learn from these kind of out of distribution examples. All right. So we talked a little bit about consistency here. I think it's something that's on people's minds, because one of the most important things about being able to learn a world model from videos is not just to get controllability. Like, I don't want to just be able to say, I'm going to press this button and it's going to move to the left, and I press that same button and it's going to move to the right. But I want these latent actions that we learn to be learned in a consistent manner, so that they should always have the same meaning, no matter what image it has been prompted to. So this will allow us to learn general behaviors if you're an agent, or maybe give you more easier interactions if you're a human who's actually stepping into these environments. So I mentioned we've seen that if we take the same prompt image, we can actually see consistent behavior. So that's what we're seeing on the right here. So given different images, these are text-generated images. We take the same sequence of latent actions, plug it into these different environments, and you see you kind of get the same sort of motion. So this is like if you take latent action 0, 5, 6, 7, whatever, plug it into each of these images, you're getting very similar trajectories, which is kind of indicating that the latent actions that we're learning are actually consistent. And again, I keep repeating this, but I think it's one of the most important things about Genie, but we're doing this without learning requiring any action labels, are doing anything like object detection or tracking or segmentation or so forth. And this sort of information would often be required to get controllable environments, but in more limited settings typically. But if you're requiring action labels or camera poses or that sort of thing, it's going to be very difficult to scale to the kind of general agents that we're becoming more and more interested in. So the most exciting thing about Genie is that we can learn these completely unsupervised from videos alone, which gives you this sort of controllability and consistency that we see here. Yeah.
Is there a trade-off between the interpretability and the accuracy of the next frame prediction? Because you constrain your whole prediction to be this like 10-dimensional action space.
Yeah.
Which does so to get interpretability, but massively constrains your prediction.
Yeah, that's a great question. Yeah, you can imagine if you increase your action space, and it's going to enable you to predict the future better because you get to see what is actually happening. But then it limits the amount of interactability that you can actually have. Like as you scale the action space, you're not going to be able to step into it and actually be able to take actions. So I would say there's a trade-off. You looked like you wanted to say something there, Jimmy.
Oh, yeah.
You disagree.
We like intensely agree.
Yes, okay.
We have experiments that show that there is this trade-off where when you increase the number of latent actions you're allowed in the model, then you get better quality prediction in comparison to ground truth.
Yeah.
But then the model becomes very unplayable when the number of action becomes like 20.
Can't you do both? Can't you swap them out? You can have a small one, train that, have a big one, and just like alternate depending on the frame when you use the big action space, the small action space.
As in like distilling it into
No, it's just like plug and play. Like at one moment you use a small one, and another moment you use a big one.
But yeah, I guess you would have to figure out when to use those two different action spaces, right?
Right.
Yeah, I mean, it is something we could try.
have a slide at the end which explains how you might be able to implement this yourself. So maybe you can.
Yeah.
We were very excited to see your future oral award for this.
I'll cite you guys.
Please do. One other thing we see is that we're able to get this sort of motion parallax effect for free just by taking the same 4 latent actions and plugging them into the same frame. So you can see that objects that are closer are moving quicker than objects that are further away, which kind of makes it feel like you're in this like 3D setting. So now, of course, it's not all about fun and games because Genie is a general method. We can essentially plug in any video data set and try to learn a world model in that setting. So we trained Genie on action-free robotics data as shown here, and again, found that we were able to learn consistent latent actions and can even simulate deformable objects. So you see here again that if we take this sequence of latent actions that's shown on the left and plug them into different images, you see similar motion, which is indicating that the latent actions learned are consistent. So you can imagine in the future, we can train Genie in even more realistic settings and obtain a foundation world model for training generalist agents. And I would say this is one of the most exciting things. I say many things are exciting about Genie, but this one I'm actually, this is like kind of my area of research, so I find it very, very exciting. So this is something that we can try out. So essentially using Genie as a foundation world model for training reinforcement learning agents within, for example. Now, of course, if we go in that direction, there's a lot of challenges that we need to figure out, including the age-old question of where does the reward come from? But as an initial step in this direction, we show in the paper that we can take a trained Genie model and use it for training agents to imitate from videos alone, essentially. So to do this, what we do is we take a latent action model that's been trained from internet videos, so that same action model that we were showing before, and we can use that to label unseen videos. So in this case, we're doing coin run or from the ProcGen environment. And so if you're familiar with VPT or prior work such as behavioral coding from observation, what we're doing is we're labeling our videos with our latent actions rather than real actions, what they do there. And then we train an agent to imitate those latent actions. And then during inference time, what we can do is we can roll our policy and try to essentially map our latent actions to real ones using a small action labeled data set. And so what we found is that this requires very few expert samples in order to learn to adapt your latent action space to your real ones, which again is telling you that the latent actions learned are consistent because we're able to directly map latent actions to actions in the environment. So how did we get here? Well, not surprisingly, we found that scale was one of the most important components for achieving high performance with our approach. So given a fixed amount of training steps, our model scales gracefully in terms of both model size and batch sizes. In particular, as we increase the size of both of these components, you can see a clear drop in loss. And so this intuition is what led us to scale our model to our final 11 billion parameter Genie model. And we also scaled our batch size to 512. Now, we realize not everyone has access to this sort of compute, but never fear. We also have a case study in the paper that allows you to train your own little Genie model with only a single mid-range TPU in under a week. So to do this, we collect examples in the coin run environment, and then use those to train a smaller tokenizer, action model, and dynamics model. And so with this approach, you can start to see very consistent latent actions. So what you see here on the right is if you take each of your latent actions and plug them into different environment initial prompts, you see similar behaviors happening again. So if you take latent action 0, nothing moves. If you take latent action 1, the character jumps and so forth. So this is a really good way to have like a sort of proof of concept, and then you can build upon that sort of work. So yeah, this is something that you're interested in. Feel free to email us and ask questions if you get stuck along the way. And yeah, I think that's all I have. So I'm going to pass it back to Jack to wrap it up.
Hi again. Hopefully I get 2 rounds of applause, which would be very nice to come back. So kind of going back to the very beginning, and well, in 2 ways actually, because we're going to talk about, I guess, the progression of agent training in our field. So really only 11 years ago, which isn't actually that long ago, I know it may seem like a long time, we were kind of training agents in single environments, and in a few hours, maybe with modern compute, we have an agent that could probably solve those environments. 2016, I remember this, like, so it seems much more recent than that, but we had a superhuman agent in Go. And so there we had a single competitive board game, and with a few weeks of state-of-the-art compute, you can get a superhuman agent. And really, if you ran it for any longer, it's quite unlikely that it would discover anything really new. And now 2023, so when I first joined DeepMind 2 years ago, we're working on this XAND project. We were looking at sort of like 3D worlds and like training across multiple different domains and getting a single agent that could do all of these things. And that was just crazy at the time. But now that seems, I guess, unexciting when we have all these new models coming out every few days. But even that, if you train an agent that can solve all these different environments, it probably is only a few months before it can't do anything new or really surprise us in any way. And all of us here in the Open-Endedness team at DeepMind, led by the one and only Tim at the back. And so what we're really interested in is algorithms that we could run forever that would keep discovering new interesting things that are both exciting, novel, and learnable for ourselves. And so what we really want is think in the future, how could we have some process where we could just run it for maybe years and it would keep doing new things? And so what we're imagining and how Genie fits into this is that you might have just this unlimited distribution of environments. You might be able to sample any possible world from this environment, and it will look like the real world because it will come from our real videos. So it'll be grounded in things we find interesting already. We can then do something like learn a reward function, because Ashley mentioned that's another challenge, but tons of folks are working on reward models. So that's an exciting and really fast-paced area of research. And then we could do something like ADA and give the agent a few shots to try and learn the action space, the reward, and solve the task. And if we run that forever with some kind of curriculum over tasks that we've also talked about in previous talks, then maybe we discover both a really super generalist agent, but also really interesting worlds that could get created along the way. And I think this may seem a little bit far out there, but I put 2025, not 2024. So it's a whole year away. And if we think of 11 years ago, we were unbelievably mind-blown about just solving breakout with the breakout simulator. And if we think about something like Genie, this really is the worst it's ever going to be, because there's more videos updated to the internet, I mean, including this talk, every day. And then computers are getting cheaper and new ideas are emerging all the time. So this really is the worst it's ever going to be. And so we really think it's quite possible that this will be the future very soon, maybe even next year. So with that, hopefully lots of awesome questions. Thank you very much for your time. And yeah, look forward to discussing.